In today's video, we are going to be discussing alkenes, and here we have the outline of what we'll be discussing. What are alkenes, isomerism, and chemical reactions? Firstly, what are alkenes? Alkenes are unsaturated hydrocarbons. This means that they have the ability to undergo addition reaction. Since they are unsaturated, it means that they can take more substances than they already contain. Alkenes form a homologous series with the general chemical formula CnH2n, where N starts with the number 2 and it goes on in that order. So the first member of this homologous series is ethene, which is C2H4. In terms of hybridization, this group of compounds exhibits the sp2 hybridized orbital, and the functional group is a carbon-carbon double bond. Now, let's take a look at the form of hybridization carried out by this group of compounds. In the first video of this series, we considered the three types of hybridization carried out by carbon atoms, and we looked at sp3, sp2, and sp. Now, the sp2 hybridized orbital is made up of 3 subshells. So we have something that looks like this. 3 subshells with 3 electrons. Now the unhybridized p subshell, which is 2pz, remains unhybridized, while this is sp2. Now these hybridized orbitals are able to form sigma bonds, while the unhybridized orbital forms a pi bond. Okay, so of these 2 double bonds, one is a sigma bond and one is a pi bond. Now, generally, sigma bonds are stronger than pi bonds. So the presence of this pi bond makes alkenes more reactive than alkenes. Now, let's take a look at how the bonding takes place. So, using ethene as an example, that is C2H4, the structural formula looks something like this, with 2 hydrogen atoms attached to each carbon. Now, the carbon-hydrogen bond that exists here is a sigma bond, and 1 electron from the carbon binds with 1 electron from hydrogen and it forms a sigma bond. The bond that exists here is also a sigma bond. 1 electron from hydrogen binds with 1 electron from carbon and it forms the sigma bond. The second sigma bond is the bond between the carbon and the other carbon. So this bond, one of the bonds, now so it binds and forms a sigma bond. Now for this unhybridized electron, overlaps with the unhybridized electron of the second carbon and it forms a pi bond. So this is how the bonding takes place for alkenes. Now, having looked at this, let's take a look at isomerism for alkenes. Now, in our first video, we also looked at the concept of isomerism, where we stated that isomerism is the existence of compound with the same molecular formula but different structural formula, or the same molecular formula but different structure. So the way in which which the atoms are arranged may be different, the position of a particular functional group may be different, and the geometry may be different depending on what type of isomerism is present. Now, alkenes undergo or alkenes exhibit three main types of isomerism. That is the structural isomerism, positional isomerism, and geometric isomerism. So we'll take a look at each of these forms of isomerism. Now, firstly, starting with structural isomerism, what exactly does this mean? Now, structural isomerism basically deals with how the atoms are arranged. So, the arrangement of atoms. So, given a particular molecule, take for instance C4H8, which is an alkene by the name butene, a structural isomer of this particular molecule would give us an idea of whether the four carbon atoms are arranged in a straight continuous chain or if they are branched. So let's take a look at this. Now, if we have a structure that looks like this, with the hydrogen atoms attached, and of course we know that carbon is tetravalent, so it would always form four bonds, so we would fill in our hydrogen atoms to look like this. Now, for this first structure, we have a continuous carbon chain that is made up of four carbon atoms. Now, in a situation where we have this chain to be branched out at a position like this, so we have a continuous chain of three carbon atoms and we have a branch of one carbon atom, but the molecular formula is still C4H8 because in total we have four carbon atoms and 7 hydrogen atoms. So the double bond would exist here and we would have something like this, hydrogen attached in this manner. And when we count through, we would still have exactly 4 carbon atoms and 8 hydrogen atoms. So we have 1, 2, 3, 4, 5, 6, 7, 8 hydrogen atoms. Now, these two molecules exist as structural isomer. So the structural isomer of alkenes basically has to do with whether it's a long continuous chain which is branched or unbranched. So depending on the branching, molecules of a particular alkene could form various isomers. Now let's take a look at positional isomer. Now for the positional isomer, this has to do with the specific position of the functional group. Now, earlier stated was that the functional group of the alkene is a carbon-carbon double bond. Now, the position of this double bond may vary for a given molecule, and we would also take C4H8 as an example. Now, drawing out this structure, if we have something that looks like this, and of course we'd fill in our hydrogen atoms, and then we also have something that looks like this. Now notice that these two molecules, there is no bond here. Okay, has 3 already. Now notice that these two molecules have the same molecular formula, which is C4H8. However, and they also have the same structural formula in that we have a continuous carbon chain that is made up of 4 carbon atoms. So they have the same structural formula and the same molecular formula. However, you would notice that the position of the functional group, which is a double bond, varies. Now, the double bond here exists between the second and the third carbon atom, while in this case it exists between the first and the second carbon atom. So if we were to name this would be called but 2 in, because the double bond is at the second carbon atom. However, in this case, the double bond is at the first carbon atom, so this would be but 1 in. This is an example of a positional isomer, and how we can see it is that the position of the double bond changes. This is a positional isomer. So let's move. So we're done with the structural isomer and the positional isomer. Now let's take a look at the geometric isomer. Now the geometric isomer exists in 2 forms. It exists in cis and trans form. For this example, we'll take a look at ethene, which is C2H4. Now, in a case where we have a particular substituent, so if we have a substituent or a heteroatom that is arranged across the carbon with the double bond. So let me just write this down. We have C2H4 and it looks like this. Okay, this is C2H4. Now, in a situation where we have a substituent or a heteroatom, so let's take our substituent to be chlorine. Okay, and we have chlorine arranged in these 2 manner. So we have chlorine arranged like this, in this way, and we have chlorine arranged in this way. So C H H and then Cl, Cl. Now notice that in this case the chlorine atoms exist on opposite side of the double bond. So this chlorine atom is on top and this chlorine atom is below, and if we are to draw a line connecting them, it would be a diagonal line. Now let's take a look at this. Notice that the chlorine atoms exist on the same side of the double bond, so they are both below the double bond in this way. And if we are to draw a line connecting the 2, it's a straight line. Now the first example that we have here, that is this particular one, is a trans isomer, and this is a cis isomer. So if we are to name this would be trans 1,2-dichloro ethene. And the second example that we have here would be cis 1,2-dichloro ethene. This is to indicate that these atoms exist on the same side for this case, and this is to indicate that they exist on alternate side or opposite side. While this is below, this is above. Now it's good for us to take note of the fact that due to the presence of the double bond, rotation is hindered, so there is no rotation. Now, the double bond hinders rotation, and that is why we can't have chlorine rotating upwards and transitioning into a cis isomer, because if rotation were to be permitted, then if we have a molecule that looks like this, that looks something like this, the chlorine here would be able to rotate such that it would take the position of hydrogen and then form a cis isomer. However, the double bond prevents any form of rotation. It's good for us to take note of that. So we are done with structural isomers, positional isomers, and geometric isomers. And for alkenes, this is all on isomerism. Now let's move on to the chemical reactions that alkenes undergo. Now, alkenes undergo various forms of chemical reactions, but for this video we'll be looking at addition reaction, polymerization reaction, and combustion reaction. Now let's start by looking at the addition reaction. Now for addition reaction, we'll be looking at halogenation, hydration, and last but not the least, hydrohalogenation. Now let's start with halogenation. So halogenation is just simply the addition of a halogen. Okay, simply the addition of a halogen to an alkene to form a substituted alkene. So when an alkene undergoes a halogenation reaction, what is formed is a substituted alkene. Let's take an example with ethane, which is C2H4. The structural formula looks something like this. Okay, we have hydrogen attached here in this manner, and then we want to add chlorine to this. Okay, so chlorine looks something like this in its molecular form. Now, the bond that we have here, the line indicating the bond here, is actually made of one electron from chlorine, so from this chlorine, and one electron from this chlorine. Now, these two atoms share the bond covalently. Okay, now what happens is that the bond that also exists here is one electron from this carbon. So we have one electron from this carbon and also one electron from this carbon. Now, in order to break this bond, we can imagine this in the sense that these carbons individually retract the shared electron. So this particular carbon, this carbon takes its electron and this carbon takes back its electron, but not to itself. Now this chlorine also takes back its electron, but in this case it now shares with this carbon and this shares with this carbon, so it forms something like this. So now we have a bond between this carbon and chlorine, and of course the sigma bond still exists. We have between this carbon and chlorine, and of course our two hydrogen atoms are still in place. Now you would notice that what we now have is a substituted alkene. So our result is 1,2-dichloroethene, which is a substituted alkene, as we have said earlier. Now this is a simple example of halogenation reaction. It's an addition reaction. Now let's take a look at hydration. Hydration is simply the addition of water molecule to an alkene. Okay, H2O. The addition of water molecule to an alkene. Now this reaction is of course catalyzed, and it takes place in the presence of an acidic medium. It takes place in an acidic medium, and an acid serves as the catalyst, more or less like the catalyst in this particular reaction. And this reaction is important and essential because it actually leads to the production of alcohol. Okay, so it leads to the production of another organic compound that is of importance. Now let's take a look at the reaction between ethene and, so we're making use of ethene, C2H4. Then we have something like this, the structural formula, or rather, before we get to this point. So the structural formula looks something like this. Okay, we have our hydrogen atoms distributed in this manner, and then we have water, so plus H. I will indicate water as H plus and OH minus. Okay, now the product. So of course we know that we have the double bond here is formed. This particular bond is formed from one electron here and another electron here. Now these two carbon atoms present are electronically identical. So they are electronically identical, so we could pick any one of them to be positive and any one of them to be negative. So I'll take this to be negative and this to be positive. Now what happens in this reaction is that, so we here, of course we know that water undergoes what we call autoprotolysis or self-ionization, autoionization. So water in this case exists as an ion with H plus and OH minus, okay, due to autoionization or autoprotolysis. Now what happens is that this positive part of water is attracted to the negative carbon, and this is attracted to the positive carbon, and it forms an alcohol. Now let's take a look at the results. The result looks something like this. So of course the one of the double bond is broken, that's the pi bond, it's broken, and we're left with a sigma bond here, and then we have hydrogen here attached, we have another hydrogen here and another hydrogen here. Now this has an OH attached to it, and we have hydrogen and hydrogen. This is an alcohol with the name ethanol, and the condensed formula CH3C2OH. Okay, ethanol is of importance, but it has both industrial and laboratory uses. So this is hydration reaction of alkene. Now let's take a look at hydrohalogenation. Just before we consider hydrohalogenation, I would want for us to take a look at Macaunikovs rule. So this is I would paraphrase this rule, and what this rule says is when an addition reaction is being carried out on an unsymmetrical alkene, when an addition reaction is being carried out on an unsymmetrical alkene, and the addition reaction we are taking a look at is hydrohalogenation. So when a hydrogen halide, something like this, is being added to an unsymmetrical alkene, the hydrogen is added to the carbon atom with more hydrogen, and the halogen is attached to the carbon with less hydrogen. This is an explanation of the rule and not the rule itself. Now, what is an unsymmetrical alkene? Let's take a look at this. Okay, so let's take a look at C3H6. This looks something like this. So we have C, then a double bond here. Okay, now we have hydrogen attached here, forming 4 bonds in total. We have hydrogen attached here and hydrogen here and here. Now this is an alkene. Okay, how do we know if this alkene is unsymmetrical or not? Now, if we draw a vertical line through the double bond, so let's draw a vertical line through the double bond. Okay, just to indicate, a vertical line through the double bond looks like this. Now let's take a look at the left hand side of the line. Now, taking a look at the left hand side, which is this direction, we have 2 carbon atoms and 4 hydrogen atoms. So let's take a look at the right hand side. On the right hand side, we have 1 carbon atom and 2 hydrogen atoms. Now, to put it simply, what we have on the left hand side is different from what we have on the right hand side. This means that this particular alkene is not symmetrical. If it were to be symmetrical, then we would have the same thing we have on the left on the right. Now I'll give an example of an alkene that is symmetrical. Take for instance C2H4. Now this has a structure that looks like this, okay, with hydrogen attached in this manner. Now, when we draw a vertical line through the double bond, what we have on the left hand side is the same as what we have on the right hand side, so this is symmetrical. However, for C3H6, we have an unsymmetrical alkene. So let's apply Macaunikovs rule to this particular alkene. So we have C3H6 with the structural formula that looks like this. Okay. And then hydrogen is arranged in this manner. Now, when this molecule undergoes a hydrohalogenation reaction, that is when a hydrogen halide is added to it. So let's take hydrogen chloride. Okay. Now, when hydrogen chloride is added to this particular molecule, of course, it's added across the double bond. So it's added across the double bond. Now, hydrogen would be attached to the carbon atom with more hydrogen atoms. So for this particular molecule, the carbon atom with more hydrogen atoms is this one. Notice that this carbon atom has two hydrogens attached to it. 1, 2. Well, this carbon atom has one hydrogen attached to it, so it has lesser number of hydrogen, and according to Macauниkovs rule, we have to attach the hydrogen to the carbon with more hydrogen atoms and the halogen to the carbon with less hydrogen atoms. So this would give us something that looks like this. So we would have H, C, H, then H, and a carbon here. Now hydrogen would be here, and chlorine would be attached here, and this carbon that had more hydrogen would have hydrogen attached to it. So this is simply what Macaunikovs rule says, and so this molecule can be named 2-chloropropane. Propane. 2-chloropropane. Okay, so this is basically everything about the addition reaction of alkenes. Now let's take a look at polymerization. Now polymerization occurs when relatively small molecules called monomers combine in a particular fashion. So they combine in a chain-like fashion to form very large molecules. Okay, so let's take a look at the polymerization of ethene. Now ethene, as we know, has the formula C2H4, and its structure looks something like this. Okay, its structure looks something like this. Now, due to the fact that alkenes have a double bond, a carbon-carbon double bond, they are able to undergo addition reaction, and this ability to undergo addition reaction enables them to be able to undergo polymerization, because polymerization is a special form of addition reaction that contains very long chains of combined monomers. So a polymer of ethene would be polyethene. Okay, polyethene, or as some texts have it, polyethylene. Now this is a special type of plastic that we use in our daily lives. Okay, polyethylene or polyethylene is a plastic, a special plastic. Now the formula looks something like this. Okay, hydrogen here, hydrogen here. Of course the double bond would not be there anymore, but ethene would still have its structure. Now we'd have N out of the bracket, where N ranges into thousands and thousands of molecules that have combined together. So this is polymerization. There are various forms of polymerization, but we would not be looking at that in this video. Let's move on to combustion. Now, like every other hydrocarbon, alkenes also react with oxygen, or they burn in atmospheric oxygen to produce carbon dioxide and water vapor in the presence of abundant oxygen, or carbon monoxide and water vapor in insufficient oxygen. Now in our video on alkenes, we derived a general formula that would help us generate a balanced equation for any combustion of hydrocarbon, and that formula is CXHY plus X plus Y over 4 O2 would give us XCO2 plus Y over 2 H2O. Now let's take a look at the combustion of ethene, which is C2H4. Now comparing it with this, X is equal to 2 and Y is equal to 4. So we'd have C2H4 plus X2 plus 4 over 4O2, which would give us 2O2 plus 4 over 2H2O. Okay, so when we simplify this further, we would get C2H4 plus 3O2, which would give us 2CO2 plus 2H2O. Now this, as we can see, is a balanced equation for the combustion of ethene. We can see that we have 2 carbons on both sides, we have 4 hydrogen atoms on both sides, and we have 6 oxygen atoms on both sides. So we have been able to get a balanced formula for this combustion, a balanced equation for the combustion reaction. So this is all we have for this video on alkenes. If you enjoyed this video, if you liked this video, please give it a thumbs up and ensure to subscribe. Thank you for watching. Bye.